So in this third lecture video, I want to explore the potential function with graphs. The potential function I want to explore is this thing that we've written down as V of R. It's associated with the electric field of some charge Q. And the way we've learned sort of simply to write it down is as K Q over the distance from the charge Q. So R labels a distance. So R is a distance. And so R needs to be things bigger than or equal to 0. And you can see that if R equals to 0, V goes to infinity, right? But this is V goes to positive infinity if Q is bigger than 0, right? So K is positive already. R is a distance, which is necessarily positive or 0. And Q, though, Q could be positive or negative. But if Q is positive, then I've got the product and division with positive numbers only. So V is only positive. The potential is positive. And if I evaluated R equals to 0, I get infinity, right? But if the charge is actually a negative charge, like electrons or something, then the potential is not going to go up to positive infinity. It's going to go down to negative infinity instead, right? So this is kind of like an absurdity. And physicists don't often talk about standing at the distance 0 from a charge. You always stand at some non-zero distance away from some charge. But what this is suggesting graphically is if the charge is bigger than 0, then we can draw the potential as a function of R. Remember that R is strictly positive. So we actually, we don't need any negative R axis is what I'm trying to say, right? Because R is strictly a distance, and distances are only bigger than or equal to 0. But if you draw the function V of R when charge is positive, what happens is you get this asymptotes, right? So the potential as R goes out to infinity goes to 0, and the potential as R approaches 0 goes up to positive infinity, and you get this shape. But if you're talking about the potential surrounding a negative charge, then it's the same story with R. You only need positive values of R, but the potential actually is negative everywhere. So the potential function instead looks like this. I'm going to erase something to make this a little bit clearer up here. Okay. So in the case that we're talking about positive charge, we get this positive potential values. And for negative charges, you get these negative values, right? So here is an R value. Associated with that R value is a value of potential. Associated with this slightly closer in value is a smaller value of potential, right? And if you come really close, the value of the potential is very small in the negative sense. I mean, it's actually a large amount of potential, but it's a negative amount, right? Likewise, over here at this R value, you get this value of potential, but at this closer in R value, you get this larger value of potential, right? So it's a graphical way to think in terms of the potential. So R is a distance. If we put Q at the origin of a coordinate system. Here's a three-dimensional coordinate system. We'll put x, y, z, and we'll put the charge q at the origin. If you go out, say, let's go up the z-axis by some distance called r, right? The potential here is a certain value. But if you go out the very same distance r on the x-axis, you'll get exactly the same potential. And in fact, actually, if you just stay in the x, z plane at the distance r, then this is all the same value of potential. But likewise, if you stay in the zy plane at the distance r, it's all the same potential. What I'm drawing out, actually, let me clean it up. So, since the potential is the same if we stay the same distance r from Q, this is suggesting spheres of constant voltage. So if the charge is positive, then the potential will be positive, right? But let's say, so yeah, and I'll just say that. I think that you know what I'm trying to say. So these spheres of constant voltage, you're going to learn that these spheres are referred to as equipotential surfaces, equipotentials. So everywhere at the same distance r, which is a sphere, right, in three-dimensional space. So if you stay at the same distance r, you only ever see the same value of potential. That's an equipotential surface. Right? So let me actually and this is a big idea. These spheres are called equipotential surfaces. Okay. You don't necessarily always get spheres, though. Equipotential surfaces have a shape that depends on the charge distribution. Right? It depends on how the charge is distributed. So here's an example. A dipole example. Okay. So actually, before I get into the dipole example, I need to say something else. So let me say something really quick. So we had V of R, right? But let's study the potential when we write R as the square root of x squared plus y squared plus z squared, right? So we can study V of x, y, and z. So this is k times q over x squared plus y squared plus z squared, all raised to the 1/2 power. That's what's meant by square root, right? So let's study this function if we stay on the x-axis. So if we stay on the x-axis, that means that y is equal to 0 and z equals to 0, right? So that's what's meant by staying on the x-axis, is you just always set the coordinates y and z to 0. So v of x comma 0 comma 0, right? So we're setting y and z just to have these values, 0 and 0, is equal to kq over x squared square root. And you have to be really careful because the square root of x squared is not x. The square root of x squared is this, right? The square root of x squared is actually the absolute value of x. The instruction here was to square x first. It says to square it first and then take the square root after, which means that squaring x first gets rid of a minus sign if there was one. Then taking the square root is always okay because we're only ever taking the square root of a positive number. So that means that the result of squaring then square rooting is only to give back the absolute value of x, right? So in that case, all of a sudden we've got a really interesting potential function. It's this. And so this deserves to be drawn really quick. So if we agree to stay on the x-axis only, so y equals to 0, z equals to 0, then the potential function as a function of x is actually symmetric about x equals to 0, right? This is different. So compare, for reference, v of r, and where r was only ever allowed to be bigger than or equal to 0. But in the case of x, right, we need to be careful. We need to think about the fact that you can be on the negative x-axis. There is no such thing as the negative r-axis, because r simply labels a distance. Okay, so now I can show you this example of a dipole. So remember, a dipole is a situation where you have a charge q and a negative of the same amount of charge separated over some distance along some axis, right? So in this case, I'm going to set the axis of the separation of these two charges, or the dipole's axis, as the x direction. And I'm going to talk about the potential along the x-axis. So the potential along the x-axis, right? So let's talk about that. So if we, let me draw you what it's going to look like. So let's do this. So the potential is this axis, and it's the net potential. It's the potential of both charges added together, but only so along the x-axis. So what this means, let's put the positive charge over here. Actually, I'm going to draw the positive charge as a little blue thing. And I'll draw the negative charge as a little red thing. And I'm going to put them symmetrically on either side of the origin. And then I'm going to draw the graph in black. So around close to the positive charge, right, along the x-axis, I know that the positive charge has positive values of potential that are going to go up to infinity if I get too close to the charge. So that's what the potential looks like over by the positive charge. But over by the negative charge, I know the potential goes down to negative infinity instead. So close to the negative charge, it looks like this. But if these are genuinely the same amount of charge, if you go and you add up the potentials here, you'll get a positive contribution to the potential because of the positive charge. You'll get a negative contribution to the potential because of the negative charge, but you're the same distance away with the same amounts of charge. So at the middle point, the potential is going to be 0, right? You get a cancellation of the potential in between for a dipole. And then on the outside, though, like the potential is just going to stay positive on the right-hand side of the plus charge. And the potential is only ever going to stay negative on the left-hand side or the negative x-axis side of the negative charge. But in between the charges, the potential has to switch from being negative values to being positive values, right? But what this is suggesting actually is imagine that there actually also is a y-axis. So let me draw you, what if we considered x and y locations, but kept z equal to 0, right? Then we need to draw the x and y axes. So I'm going to draw them in this kind of like strange way. So here is, I'm going to draw the y-axis here. And I'll draw the x-axis here. Right, you can kind of see that the y-axis heads back into the screen and the x-axis is heading over to the right but out of the screen. And I'll draw in the perpendicular direction, not the z-axis. Like if we were drawing 3 dimensions of space, this third direction would be the z-axis. But I don't want to consider z-axis differences. So I'm just going to keep the z value the same value, just an easy value is to consider 0. And instead, this axis we'll label the potential. And this potential is a function of x and y, right? And so if you do this, let's put the charges down again. So here's the positive charge. And this time I'm just going to draw a blue dot to represent the positive charge. And I'll draw a red dot to represent the negative charge. And I'll put it the same distance, but on the other side of the origin. So there's the 2 charges. And then I'll draw the potential. But now the potential is not going to be a line like up here, but the potential is going to be a 2-dimensional surface because it's a value for 2 dimensions of coordinates. It's going to be a 2-dimensional sort of blanket in this 3-dimensional coordinate system. So I'll draw it in black. Okay, so if I was to stay along the x-axis, so that is at y equals to 0, then we already know the answer. The answer sort of looks like this thing. So it comes up from below, crosses through the origin, and then goes up to infinity as I get close to the x location there. And then behind the charge, I come sort of up this funnel towards the negative x-axis, and on the positive x-axis, sorry, it's hard to draw like this. But if I come out in the y, right, the y direction, what I'm going to do is going to sort of fill out these funnels. These are actually funnels around the asymptote. right? You can, if you want, go figure out the shapes of these things, but I hope you can see. Actually, this goes out to infinity. So the 0 goes out to infinity and comes back kind of like this. So yeah, and this 0 goes out to infinity, but yeah. Okay, so so this potential function is a surface with two funnels. One of the funnels goes up to positive infinity in potential, and the other funnel goes down to negative infinity in potential, right? But each of these rings is an equipotential. These are rings of definite value of potential that's all the same. So this xy coordinate has this value of potential, but so does this other xy coordinate and this other xy coordinate. So all of the xy coordinates along this ring is an equipotential, right? It's the same value of v for all of those different xy coordinates. But this is a ring in xy. If you add in being able to move around in z, they won't be rings anymore, that they will be little surfaces of their own, and they will become equipotential surfaces, right? It's sort of hard to think about these things because in order to draw v, x, y, and z, this is 4 axes, right? This is a 4-dimensional thing to think about. So you sort of run out of that ability because we tend to not be able to draw things except for in 3D. Okay, so that's what I wanted to describe in this small lecture. Thanks for listening to me.